everybody, and welcome to The Perando Show, the most lit math podcast on the internet where we explain basic mathematical concepts in the blink of an eye. We hope you have a mathematical day. Today, we have invited Mr. Ardee Perando to explain the first fundamental theorem of calculus. Hello, Mr. Perando.
Hello, Claire. Happy to be here. The fundamental theorem of calculus is a theorem that links the concept of differentiating a function with the concept of integrating it. And as its name says, it's one of the fundamental building blocks of calculus. And this is how it works. Let's define a function f which is continuous from the interval a to b. And let's label that y equals f of t. Let's define another function, capital F of x, which is the integral of f of t dt from a to x, such that x is between a and b. We know that definite integrals are basically areas under the curve for a certain interval, and we can see that here in the graph, which is the area under the curve from a to x. If we were to take the derivative of this function, capital F of x, by limit definition, we are going to arrive at this expression. We can then substitute the first equation to this second equation, and we are going to arrive at the limit as delta x approaches 0 of the integral of f of t dt from a to x plus delta x minus the integral of f of t dt from a to x all over delta x. Again, definite integrals are areas under the curve for a certain interval. So we can see here that the numerator is basically the area under f of t dt from a to x plus delta x minus the area under f of t dt from a to x. Graphically, we notice that it's basically just the area under the curve of f of t from the interval x to x plus delta x. We can then simplify the equation into that. And let's label it equation number 1. Leaving that aside for now, according to the mean value theorem, there exists a c between x and x plus delta x such that f of c times delta x is equal to the integral of f of t dt from x to x plus delta x. We can then rewrite that equation into f of c equals 1 over delta x times the integral of f of t dt from x to x plus delta x. That means that there's some number c between x and x plus delta x such that if we make a rectangle with base delta x and height f of c, that will result to the same area as the area under the curve from x to x plus delta x. Now we can use equation 2 and substitute it to equation 1, resulting to the derivative of capital F of x equals the limit of f of c as delta x approaches 0. Now all we need to do is evaluate this right side of the equation. Now remember that c is between x and x plus delta x. Now if we take the limit of the left and right side of this inequality, the limit of x as delta x approaches 0 is simply just x since it does not depend on delta x. The limit of x plus delta x as delta x approaches 0 is then equal to x. Therefore by squeeze theorem, the limit of c as delta x approaches 0 is also equal to x. Now since c approaches x, f of c approaches f of x, and the derivative of capital F of x is then equal to f of x. Now since we showed that the derivative of capital F of x is equal to f of x, we have just proved that integration and differentiation are inverse processes as stated by FTC 1.
Wow, so that's what the first fundamental theorem of calculus is. Amazing! And with that, we'll get back to you after the break. Welcome back to the Perando Show. Mr. Perando has just explained FTC 1, or the first fundamental theorem of calculus. Now, we're going to give away an Uno in math and 500,000 pesos to the caller who guesses the person who first thought of the FTC 1. Hello, you're connected to the Perando Show. For an Uno in math and 500,000 pesos, who first thought of FTC 1?
Newton and Leibniz both used different methods to develop the fundamental theorem of calculus. Newton used fluxional notation, whereas Leibniz used differential notation. And although right now differential notation and differentials is what is used, I believe that Newton was the one who invented the fundamental theorem of calculus because he was the first one in terms of evidence to write it down. Newton developed his fluxional notation in 1666, as can be proven by documents, whereas Leibniz's first documented use of differentials was in 1675. In addition, it had been proven that in the intervening period, the two of them had communicated about calculus and the development of it. And it was in 1684 that Leibniz first published a paper about calculus. So, in conclusion, although Leibniz published first, I believe that, as it can be proven and documented, Newton was the first one to develop calculus using fluxional notation.
It appears that we have another caller on the line. Putting you on now, sir.
So let's talk about the controversy from Leibniz's perspective. First of all, at the end of the day, Leibniz published his paper first in 1684 versus Newton, who submitted his paper in 1693. And even then, it was just a minor annotation about tangents in his work. Second of all of the evidence against Leibniz are circumstantial and depend on him going against good faith. This includes seeing Newton's papers about tangents, which Leibniz did admit, but he said that it was of little to no value of him. It was even seen in Leibniz's papers, when it was published after he died, that he made the discovery independent to that of how Newton found out about it. Leibniz started from integration where Newton started from derivatives. And my last point is that even Newton said that one of the methods developed by Leibniz, the power series, was new to him, further strengthening this point.
Wow, so that's
Leibniz pa rin mga ulol!
Anong Leibniz pa rin mga ulon? Mas mauna pa rin si Newton kaysa sa'yo.
Anong mga pinagsasabi ng Newton na to? Original to, the original!
Tignan natin sinong nagsalita, yung mga ngopya, no? Hindi porket ikaw yung naunang nag-publish, yung idea nagsimula sa'yo.
Di porket Newton pangalan mo, bago na lahat ng idea mo!